right. Hello, everyone. First, just going through introducing myself very quickly. I'm Philippe Pepin. I'm originally from Quebec. I am originally a civilist, but have been specializing in intellectual property over the last 5 years. I've been involved in the intellectual property management of Hankeni School of Economics in Helsinki, starting 2013. I've been involved with the European Institute of Technology in the digital sector, producing educational material, and I've taught in multiple universities in Finland and in China. Today I'm here to bring a bit of this international perspective to the topic of the energy transition, and more specifically, putting energy storage as a challenge in relation to what are the grand ideas at play, what are the great forces at play here, what do we actually need to do if we want to reach our climate objectives. So, as we all know, the IPCC has been quite alarmist in the last few years, trying to bring us to have some change in the way that we do, that we consume energy and produce energy. The ultimate goal is to go carbon neutral eventually, and to even be carbon negative in the way that we produce energy and consume it. Today, again, my 3 objectives are first to bring you an understanding of what exactly is the scale of the challenge we are playing with. I also want to bring you some of the topic areas that we deal with at Teraloop, so ideas that help us go towards the design of the technology that we do in-house. And finally, I want to get you involved, so getting you interested in developing new ideas, developing new prototypes, bringing new technologies to the market, because this has to start now. Then, again, today, there's 3 segments to my presentation. I will first go through the scale of the challenge. I'll discuss about how Teraloop approaches the challenge of energy storage. And finally, I'll give you some ideas through the story that we have at Teraloop in terms of product design and implementation. So, just how big is the challenge that we are dealing with at the moment? I believe that most of you already have some sort of general idea about what are we playing with in terms of energy storage. We all know that it's very complex, it's very multifaceted. There's different there's different market segments that must be addressed by different technologies. So we have the short-term power management segment that is usually tackled by flywheels, batteries, supercapacitors, ultracapacitors. We have the medium-term energy storage, which is the daily markets. So we're talking about 4 to 6 hours. This is typically met mostly by lithium batteries, also flow batteries. Some flywheel technologies in the world are also addressing this. And finally, we have the seasonal storage, which is addressed, amongst other things, by compressed air storage, pumped hydro, power to gas, which is a big topic right now. So the question today is, what is the specific subject matter that I will address? And it is the daily energy markets. So we are talking about storage technologies that can provide cycles of storage of 5.5 hours. We like to say also 4 to 6 hours. It depends on the area in the world. This is by far the largest market segment in terms of throughput of energy. And to understand just how big this market is, there is very interesting data that has come out recently. I don't know if any of you are familiar with the Hooratta University of Technology, or if you are familiar with the Energy Watch Group in Germany. They have jointly produced this first effort worldwide in 2017 of techno-economic analysis, trying to understand just how much energy can be produced over 145 different regions of the world. How is it stored, and how do we optimize this system? A number of great ideas came from this. The most interesting one is that if in 2050 we want to be realistic about solving this challenge, we have to take into account that we're going to be about 9.7 billion people on the Earth. And we have to take into account that the demand will continue growing. So if we look at the different market segments, we know that of all the scenarios studied, if we utilize renewable energy mixed with storage, this is more affordable than any other scenarios that involve fossil fuel and nuclear energy. So any pennies that we are spending now on something else than this renewable transition is essentially a very bad idea. The other interesting idea that has come out of this study is that we already have the technology and we already have the business models to be able to deploy this technology. So in essence, the thing drawing us back is political will. So this is another interesting topic. In any case, the specific market segment of daily storage, we're talking about that 30% of all the renewable energy produced in 2050 will pass by an energy storage asset. Most of it will be through the daily storage. So in 2050, also, we have to talk about 48 terawatt hours of daily energy storage capacity. This is a gigantic amount of energy storage. To put things in perspective, as you can see, this is the overall energy storage capacity needed in 2050. The big square on the left is the daily storage market, and the small, it's quite invisible actually at this resolution, square on the lower right is the current capacity. So we're talking about a gigantic challenge, which will have pressure environment, materials, and many other things. To give you an idea of the development, so as you can see, there is quite a present need to start investing in those technologies. A concurrent study that has come out by Bloomberg establishes a different scenario. So they're not talking about 48 terawatt hours, they're talking that realistically, considering the current market forces, we can talk about roughly 2.8 terawatt hours. So we're talking about a scale of, by 2040, almost 10 times smaller. This still represents an opportunity of roughly $680 billion by 2040, which is quite a large scale of investment needed to be able to meet our objectives in terms of growth. This is where we come in. Teraloop is a kinetic energy storage company established in Finland since 2014. We were established as part of the Aalto cluster of innovation. We have 5 co-founders, most of them Finnish, and a Canadian and a British person. We've grown over the years to a current full-time equivalent of about 12 people. We have went through quite a lot of iterations of the design of the product that we're doing. And currently, I must say that the future looks quite good for us. And I'm going to get back to that in a moment. What we are doing is we're meeting the daily market via mechanical energy. Our vision is that in the future we have to aim for a fully renewable electric generation. There's no other path towards the future for us. We are also strongly directed by the different sustainable development goals by the UN. Our mission is to build sustainable grid-scale stationary storage, and we want to serve the daily market for the energy supply. This is first in order to allow the penetration of variable energy into the grid, and this is secondly to enable a zero carbon emission electric generation as part of the global objectives that we've put forth over the last few years at the different meetings, such as the Paris goals. There are different specific topics of interest that are very important to us, and that we think every energy storage technology should take into consideration when developing their product. The first one is that in the future, if we want to truly make a positive impact with our technology, we need to have the lowest impact in terms of carbon emission per energy throughput. What that means is that any asset that we deployed needs to have a very high level of efficiency and needs also to have the highest amount of cycles of charge-discharge before the asset must be decommissioned. If we compare, for example, lithium batteries can have up to 8,000 cycles. It's likely to continue rising, but not that much in the future. Flow batteries have what we call unlimited cycling, which in reality means about 20,000 cycles. When it comes to mechanical storage, such as Teraloop or other flywheel technologies, we're talking about a number of charge-discharge cycles that starts at 250,000 cycles. It's just a different scale of sustainability. And when it comes to efficiency, kinetic energy storage, such as a flywheel like Teraloop, remains to this day some of the most efficient energy storage technologies available in the market. The second topic is that we need to be able to have more energy stored with the least amount of material possible. How we've implemented that in our technology is our flywheel is a hubless device, which means that we've eliminated all the dead mass in the middle, which has enabled us to be more scalable. It has also enabled us to store more energy with the same amount of material. Furthermore, if we look at the future needs, if we look at 48 terawatt hours of capacity, we need to be able to source that from different sources of raw materials. We can't deploy all of that with only lithium. There needs to be different sources because whoever controls the sourcing of lithium will have quite a gigantic economic power. We're already talking about a new OPEC in South America, for example. This is a real possible, a real tangible shift in the power worldwide. Teraloop currently relies on two core raw materials, carbon and steel, both totally recyclable and totally reusable. The next step, the next key topic that we have in designing our technology is we have to understand how to lower the cost of ownership for whoever is going to deploy this technology. Currently, if you follow the news, you'll understand that, for example, flow batteries, which are another quite capital-intensive technology, have started to push forwards for new models of ownership. So there's, for example, rental of batteries. There's also renting an electrolyte. In the future, we're going to talk about energy storage as a service. So there's different ways to lower the cost of energy, lower the cost of ownership, to reduce the risk of whoever is paying the upfront cost for the technology. And then we need to start being more honest about what we disclose to potential investors in this technology, about what can be realistically expected from this technology. Currently, there is a lot of misinformation in the battery world. So we're talking about very variable costs. The costs that we see in the media are usually not exactly the costs that are the real costs. So, for example, at the moment, a lot of the batteries are sourced in South Korea, sold underpriced to manage to keep the market share. So we don't know exactly what is the real cost of that technology. And we've saw some false advertising claims that have started to come up recently from some of the battery manufacturers. So we have to ask ourselves the question, what is really the realistic expectations we can have from this technology? The same goes for the durability of those batteries. So if we talk about 15, 20 years, such as what is disclosed right now, is it 15, 20 years with 2 to 3 charge cycles per day, 1 cycle per day? Is there an overspecification of the asset? And what impact does that have on the material sourcing? So these are all relevant questions that people take into account when purchasing new assets. We see a strong rise right now of companies that offer these battery life value assessments. Then the other one is designing for circular economy. That's a very important topic for us as well, because as I've mentioned multiple times, if we look in the future, 48 terawatt hours of capacity, this is not a fleet of lithium batteries that we can simply discard and replace. We have to find a way to recycle and reuse the same materials within the same value chain. So, at Teraloop, we're involved in a number of projects, actually, with regards to circular economy. A good first example is the recycling of rare earth magnets, because there is a need for rare earth magnets for the levitation of our rotor. In Finland, there is this project called BAT Circle, which is specialized in pushing global knowledge in the recycling of lithium batteries, because at the moment, there isn't a way to recycle those assets. We are also involved in developing new technologies around magnetically loaded carbon fiber, bio-based carbon fiber, to be able to reduce the amount of critical raw materials such as neodymium magnets, and to be able to rely on different value chain than oil and gas. Now, to finish, the last segment I have for you is to just give you an idea of what's the life of Teraloop at the moment. So this is the current team that we have, roughly. We are based in Helsinki, in the Hankeni campus. If you're curious to come and discuss with us, I can organize some visit of our offices. As you can see, the machine is at the bottom. We started in 2014, 2015, where we utilized the National Research Institute of Finland, VTT, to pursue some simulations which have led to an original patent, which was quite different at the time from our current configuration. The results from VTT were then evaluated by pöyry, which have come with the conclusion that our claims with regards to the market and with regards to the technology potential were accurate, which means that we were able then to start prototyping. Our first prototyping was in November 2016. This is a half-meter prototype, and it showed most of the subsystems that we have. And as you can see, there is a levitation that keeps the circular rotor levitated, and then we have a number of coils that accelerate and decelerate the rotor. Once we've built the understanding with this, we have obtained investments from Japanese company Yaskawa Electric Corporation, and with them we funded the next iteration, which is the currently largest flywheel in the world, being hubless. This is the vacuum chamber being delivered in October 2017. We then received the rotor. So for those of you who know anything about flywheels, this is a hubless rotor with a band of iron around it for the electromagnetic stabilization of the device. And then we have a number of permanent magnets bonded to the rotor, which can be utilized for acceleration and deceleration of the motor. We then assembled the machine back in December 2017, and today we can show the device operational. So this is only 30 RPMs to be able to have you guys see the electric tape going around, but this is the largest hubless flywheel in the world at the moment. And in 2024, our objective is to start addressing the market for utility scale energy storage or daily energy storage. This is a graphical representation of what could an asset of Teraloop look like in the future. So we're talking about putting the flywheel under the ground, having ground transportationable flywheels of a bit less than 4 meters in diameter, which is quite attainable, I would say, by 2024. So this is it. Thank you. Any questions?
Thank you very much. Fascinating stuff. So, what kind of markets are you targeting? Is it industry or more like residential areas or?
Yeah, short term, so between now and 2022, 2023, what we're targeting is power management, so very short duration of energy storage, more specifically for commercial and industrial applications. This is because currently the market for daily storage is not mature enough. So we have these traditional generation facilities that have been completely paid for and are still operational. So it would be very difficult to deploy grid-scale daily storage between now and 2025, considering the very affordable, very good rate of return people are getting from this traditional generation. So we're targeting areas where you have multiple cycles per day. So we're more economical than a lithium battery if you consider that there is more than 2 charge cycles per day. So commercial and industrial for now.
Okay, and you mentioned that you use steel and carbon fiber on the flywheel, and they are both reusable, but is that the only part you have to exchange?
No, definitely, there's copper, of course, that we need to reuse, and then there's I think the most critical part to deal with in our technology is the Neodymium Magnets, which currently we know can be recycled, and we can obtain 99% of the materials back from the process, but it doesn't really come back as a directly usable new magnet. So you come with this paste, and that's knowledge that we've obtained from this Bat Circle project in Finland. So I would say the major components we know we can reuse. The challenge is, for example, with carbon fiber, if you really want to go for this circular economy stuff, you need to be able to reuse it in the same value chain, which means that the fibers must be still reusable in the next exchange. Maybe it's not economically possible. Maybe we'll have to simply crush it and generate another one. So it's different questions that we have to ask ourselves in the future.
And what exactly is the capacity of this model, and does it scale? It seems like it takes a lot of room.
Yeah, that's one of the points actually. For this technology, we can reach just under the energy, the space used per energy that we see right now for grid-scale lithium batteries. So although this machine was built to be about 3 meters in diameter to prove a point that we can make it bigger. In reality, we are probably going to be deploying smaller devices. So the next devices we have smaller configurations planned, we have larger configurations planned. This kind of device, you could build a 20-meter diameter device that stores 10 megawatt hours, or you can store very smaller assets around the same size as this one that stores 100 kilowatt hours and has a power of 1 megawatt. So we're talking about a very high energy density for a mechanical storage system. And
okay.
This is, yeah.
Does anyone have any questions?
Thank you very much for the nice presentation. Quite interesting stuff. So I would like to know what is the weight, because that's for flywheel or mechanical energy storage, the biggest disadvantage is the weight.
Yeah. So this picture you see there, that's about 260 kilograms. But the next iteration, so the one that's going to be 100 kilowatt hours, is going to be about 1 ton of carbon fiber. A bit less than a ton of carbon fiber.
Thank you.
Yeah.
Anyone else? One more.
how much do you think you will sell like this kind of
device?
This kind of product?
Yeah.
Like in
The question is, are we going to sell devices or are we going to sell a service? Because that's what I was talking about, you know, when I talked about the cost of ownership of the assets. Right now, a lot of this renewable generation and this storage is very expensive if you pay it as an upfront cost, which is very discouraging for people who are considering to have more renewable assets. So in the future, most likely what will be the cost is going to be a monthly fee or a yearly fee or a fee of use, because what we've seen in the market is that people are not interested in buying these assets anymore. There is still some potential for the commercial and industrial segment that we are currently targeting, but when it comes to the daily storage in the future, it's quite possible that Teraloop will actually have a service rather than a product, which is quite a bit out there at the moment, considering how traditional the way the industry sees energy trading. So.
And for the normal battery, you will get a guarantee of 10 years. How do you plan to solve this with this device? Is it going to be also, if we talk about service, how long would you say it can serve for?
This technology could last more than 30 years. Quite more than 30 years. And it does not degrade with use. So with batteries or supercaps, what you see is that with the use of the asset, there's some challenges when it comes to managing the heat, which means that the same asset, the more you use it, the less usable it is in the future. We don't have that challenge, which means that if you buy a 20 years old asset from us, or you start consuming our products, you have essentially the same asset as what it originally was, which completely transforms the way that we can discount the asset from a financial basis. So you don't actually have to pay it back in 4 years, for example, the same way that a lot of British battery owners have to calculate the payback period.
And thank you very much for that.
Good.
And give a round of applause to Philippe.